Hiya folks, this is the third and final virtual lesson. We won't need to do any more online after this one. We'll have covered everything we need to have done outside of school and what's left of the topic, which is, I think it's just generators, we can obviously do in lesson. This is, as you can see, for higher combined, so it applies to whether you're doing physics only, whether you're doing the triple or whether you're doing the combined. So the first thing I want you to do is I want you to look at those current carrying wires on the top of the picture there. You can see there's one there, there's one there, there's one there, and there's one there. And I want you to have a look at each one and see which field you think should match up with each one. So do you think this conductor here should have a field like this? Which would you match up with which? Okay, think about which hand rule you need to use and which direction the currents go in, and therefore which direction the fields go in. Or, yeah, decide which hand rule you've got to use, then come up with an answer. I'll give you a second to have a think about it. Pause the video and try it out. Okay, answers incoming, so make sure you've had a think about what your answers might be. So I'm just going to close the PowerPoint for a second and open that up as a BoardWorks file. Okay, so those were the current carrying wires at the top, and then these are the potential magnetic fields at the bottom. So for this one here, I've got a solenoid, and I can see which way the current's passing through the solenoid. Remember, a solenoid is just a coiled piece of wire. So the current's coming in here, and then going round and round and round and round, and then it comes out at the bottom. Okay, so in at the top, out at the bottom. So I need to think, right, I've been given the current, but I've not been given the current in the solenoid, but I've not been given the direction of the magnetic field. So which way would the magnetic field be going? So I know I'm going to be using the second right-hand grip rule, and I've been given the current, which means I need to line up my fingers with the current on that coil of wire. Now, as I've currently got my hand like that, if I do that, that's not going in the same direction as the current, so that one's not working. So the north is definitely not up. If I do that, however, now my four fingers are lining up with the current in that solenoid, and my thumb's pointing down. So I want something that's showing a solenoid's magnetic field, which is either going to be this one or this one, and I want the one that's showing the magnetic field going down, okay, which is going to be that one there. Right, so for this next one, I've got a wire with a current going upwards, and I've got no field around it. So I need to use the right-hand grip rule, the first right-hand grip rule, which is that, and I want my thumb to point in the direction of the current, and the current's going up there, so my thumb's going up, and my fingers would curl round like that. Okay, so if I was looking at my thumb, they'd be going anti-clockwise. So it's going to be either this one or this one. Out of those, which is showing the magnetic field going anti-clockwise? Well, this one's showing the magnetic field going clockwise, so it's not that one. So it must be this one, so I'll match it up to that one. Okay, we've got another current carrying wire there. This time the current's going down, so my thumb needs to point down. And my fingers are curling round like that. And I want something where the magnetic field's going round the wire like that. And if you look at that one, the magnetic field's going round the wire like that. So I'm going to match that up to that one. And then the last one, I know it's obvious what the answer is, but let's do it anyway. So I'm using the second right-hand grip rule, because that's a solenoid again where I've been given the current. And I automatically just put my hand up like that, and I think about it. Is it going round the right way? This time it is going round the right way. You can see my fingers curl round in the same direction that the current's going round that solenoid. And my thumb's pointing up. So I want a solenoid magnetic field where the magnetic field is pointing up. It's coming out, going from north, around, and then to south. So that one would be that one. Okay, so hopefully you got those right. And even if you didn't, you've now seen how you should have got them right. Just a bit more practice there for you, so we can get to the point where this is just dead familiar and it's like common knowledge for you. Okay, right, so outcomes wise, there's no outcomes. I've put the specification there again for you. I'm going to take a minute to go through this, because I was quite surprised by the volume of content that's required for this one lesson. Looking at it, a couple of lessons would have been advantageous on it, but we'll go through each bit anyway. It works in your favour that there's a bit of crossover from P2, which we'll get to later. So I'll read it out to you, and you can kind of follow along with me. A basic transformer, so this is the stuff that you need to know on the left-hand side, the content that you need to know. A basic transformer consists of a primary coil and a secondary coil wound on an iron core. Well, you've done that in P2, that's nothing new. Iron is used as it's easily magnetised. You knew that already. Knowledge of laminations and eddy currents in the core is not required, so we don't need to know about these things. I might mention them very briefly later on. Not that you need to know it, but just as a reason to something else that you do need to know. The ratio of the potential differences across the primary and secondary coils of a transformer, and we've got VP and VS. Well, we've just been told potential difference across primary, P, and secondary, S. potential difference, voltage. So VP means primary voltage, and then VS means secondary voltage. Depends on the ratio of the number of turns on each coil, and we've got NP and NS. So the ratio of the number of turns on each coil. So N for number of turns, they both got N's, so we talk about the number of turns, P on the primary coil, S on the secondary coil. Okay, so these VP, VS, NP and NS are going to form part of the equation that we're using later on, or one of them at least. Okay, so that's the first portion done. Okay, this bit says it's got the equation. Okay, and it says potential difference VP and VS are measured in volts. In a step-up transformer, VS is greater than VP, so the voltage on the secondary coil is bigger than the voltage on the primary coil. Now, you might not have seen it written like that when you did this in P2, but you were taught it like that. Like in a step-up transformer, you've got less coils where it goes into the transformer than you have when it comes out of the transformer. That's what that's saying. In a step-down transformer, it's the opposite way around. The voltage of the primary coil is greater than the voltage on the secondary coil. So you're putting a higher voltage in and getting a lower voltage out. Step-down transformer. If transformers were 100% efficient, the electrical power output would equal the electrical power input. Now they're going to, you get this quite frequently in physics questions where they'll say like, an easier example to understand straight off the bat would be like in the forces topic where they go, oh, assume there's no friction. Well, in real life there is friction, but if we're calculating energy and then you've got to add friction into it as well, all the equations are less accurate because now you've got to account for a bit of energy loss. And let's just take it as read. We understand there's going to be some energy loss. Let's not involve it in the equation. We know there will be, but we'll calculate it as if there's not going to be, and that way we get an easier to calculate answer. So if transformers are 100% efficient, spoiler alert, they're not. They're pretty efficient, don't get me wrong, but they're not 100%. Right, next one. Oh, I'm sorry, the key thing to take from that though, if they were efficient, the electrical power output would equal the electrical power input. Okay, we'll talk about that later. Here's the second equation that we need to know about. And now we've kind of talked about these up here, what the P and the S mean. This kind of probably should make sense. VS, so the voltage on the secondary coil, multiplied by IS, the current. Remember I, old word for current was impedance, that's why the I comes from. So the voltage on the secondary coil multiplied by the current on the secondary coil will be equal to the voltage on the primary coil multiplied by the current on the primary coil. So this is trying to get across the idea of there's going to be a conservation of energy as you go from your input power to your output power. You can change the variables that calculate that power, but the actual power itself should be the same in a 100% efficient world. So power input and output is measured in watts. Okay, you know that already. You know power is measured in watts. Students should be able to explain how the effect of an alternating current in one coil induces a current in another and is used in transformers. Okay, explain how the ratio of the potential differences across the two coils depends on the ratio of the number of turns on each. And then calculate the current drawn from the input supply to provide a particular power output. Now, all that sounds really confusing. It's basically just use the equations and calculate some numbers. Okay, there's not much to that. That's fine. And then the last one, apply the equation linking the potential differences and number of turns in the two coils of a transformer to the current and the power transfer involved, and relate these to the advantages of power transmission at high potential differences. Now, I'm hoping whoever taught you P2 went through the reasons behind step-up and step-down transformers. They didn't just say this is a step-up, step-down transformer. They told you why we use them. Okay, that's an important thing to get across. I'm going to go over that again now. So even if they didn't, but you're going to find out now. Okay, so you've covered why transformers are used in P2, or you should have covered why transformers are used in P2. Remember, P2 is the electricity topic. Okay, so imagine you work at the power station, and we've got a power station here, haven't we? So imagine you work there at this power station, and it's your job to get electrical energy to homes. Obviously, in your house, you are using electrical energy for all sorts of things, aren't you? You're watching this video right now on either a phone or a tablet or a computer or whatever you're watching on, and the energy stored in that device, if it's portable, came from a charger that was plugged into your mains electricity supply in your house. If you're watching this on a PC, your PC is currently being powered by energy that's been delivered from the power station through the national grid, and it's coming out of your plug sockets now. Okay, obviously the journey is not quite as straightforward as power station, wire, house. There's other steps involved, and that's what we need to talk about today. I've written here because power equals current times voltage. You've got two choices, because remember, electrical energy measured in joules power is measured in watts, but power is talking about how much energy is transferred per second. So we're not using them interchangeably. I nearly said something wrong there. But when I'm talking about power, I'm actually talking about how much energy we're transferring in a certain amount of time. Okay. So because power is equal to current times voltage, you've got two choices. Okay. Let's say this house wants, I don't know, 100 joules of energy. That's a ridiculously small amount of energy, by the way. But let's imagine it did want 100 joules of energy. You send out 100 joules of energy from the power station. Does it all get there? How much? If it doesn't all get there, how much is lost? Do you want to be losing energy? We need to talk about how we could do this, okay? So you've got two choices. And the first choice is you could send it at low voltage and high current. So I could send it with a voltage that's very, very low, and I could send it with a current that's very, very high. Can you spot what the issue would be with this? Like, what would be the problem? If I was to use the national grid and send electrical energy out at huge currents, what's going to happen? Well, this might be a bit of an exaggeration, but something like that's going to happen. Okay, so you can see don't get me wrong, the power lines aren't going to set on fire, but they are going to get ridiculously hot. Okay, a lot of energy is going to be lost from the power lines, and that's energy that was meant to go to houses or to factories or to wherever it was going to. That would be a pretty inefficient way of transferring electrical energy. Okay, so transferring electrical energy at high current would mean the transmission cables in the national grid would get really, really hot. Hot wires equals energy loss, and that would be a massively inefficient way of sending electrical energy from the power station to houses or to factories. Remember, to get this electrical energy in the first place, we've had to either burn a fossil fuel, or we've had to use nuclear power, or burn biomass, or whatever it is that we've used to produce this electrical energy. We don't want to be wasting any of it. Like, that's obviously, we've got limited resources as it is, and doing this obviously wouldn't be the best idea. I've put a little animation on the top right hand side there, as you can see. That's a wire with a current passing through it, and given the thickness of the wire, that isn't even going to be that high of a current. Like, you know what I mean? The wire is getting visibly hot. If it's that hot, you can see light energy being given off. Would you want to touch it? No, because it's obviously really hot, so that's thermal energy being given off as well. This would be a massive waste of energy. So we don't do that. We do something else. What options left? How could we get as much electrical energy from there to there as possible in the most efficient way possible? Well, hopefully you've spotted, if your one option is low voltage and high current, well, the second option is the reverse of that, isn't it? So we want to try and transmit energy then at a low current instead and a high voltage. And hopefully you can remember back when you did this in P2, you talked about the voltages that are involved. After it's been stepped up from the power station, in the national grid, the power lines that you see between pylons, we're talking like upwards of 400,000 volts, huge voltages. And that way you can send it at really low currents. The amount of energy at the end is conserved. The amount of actual electrical energy that's delivered to customers is practically unchanged because not much of it's been lost in the wires or in the transformers. So to transmit electrical energy at low current and high voltage, we need to use transformers then. And this is a picture of a transformer there. There's really not much to them at all. So the voltage of an alternating current can be changed using a device called a transformer, and this is done with alternating current. Okay, we've talked about your domestic supply, your house supply being alternating current. Okay, alternating just means going back and forth. So the current's going back and forth. That's it. Electrons moving back and forth. Okay, and energy is transferred that way. I'm going to pause there for a second. I'm going to go off track just for a second because I remember when I was in school and I was being taught this, and it took me a minute to get my head around how it's even possible to do that. I totally understood direct current. The idea that you give an electron some energy and ask it to carry it somewhere, it goes to that thing and it gives the energy. That makes total sense to me. But how can I give energy to an electron here and then expect it to deliver that energy hundreds of miles away if all that electron does is this? It never goes to where it's meant to go. It just goes backwards and forwards. Well, think about it like this. If I got the entire class, 30 of yous, to line up in a one big line, shoulder to shoulder like that, tight as you could, and then I pushed one of you, well, I give that first person a bit of energy, and then they bump into the person next to them because they're really close, and they transfer the energy I gave them to the person next to them. What does that next person do? Well, they bump into the person next to them as well, because they've just been given some energy, so that moves them. That energy is then transferred to the next person, and it obviously shifts all the way down the line. So that's how the energy is being transferred in alternating current. These electrons are moving back and forth, but the energy is transferred from the power station to the domestic supply. It's not dissimilar to a longitudinal wave, is it? The particles move back and forth, energy is transferred from one particle to another. Think about it like that. So the voltage of an alternating current can be changed using a device called a transformer, and it contains two coils that are wound around an iron core. So this is the iron core there, and we use iron just because it's easily magnetized. The alternating current in the primary or input coil produces an alternating magnetic field. Pause and think about that. Wire carrying current creates a magnetic field. Oh, we know that. That's good. If I get that current to change direction, the field changes direction. We know that as well. We've talked about it when you take the leads out of the power supply, switch them around, and put them back in again. The field, if it was pointing north, for example, if the field was pointing north, it now points south. So we know that happens. So if you get this alternating supply, where the current's constantly going left and right and left and right and left and right, flipping direction constantly, the magnetic field is constantly flipping direction. We'll talk about why it's alternating, by the way, in school, in the generator lesson. Okay, that's called the generator effect. This alternating magnetic field induces an alternating current in the secondary or output coil. These wires aren't connected. Look at this. This has got a current passing through it, the one that's connected to my power station. There's then nothing in the middle, and then there's a secondary coil on the output here that apparently now has a current in it. How is that even possible? Now, you might be thinking, oh, right, well, it's made of iron, which is a metal, and then it conducts. These wires are insulated. They're not just bare wires. So it's not, the iron is not conducting anything. The iron just acts there to be a magnet. It becomes magnetized. There's a key term that you need to get here, okay? So these two coils aren't connected. How is it transmitted? There's a key term that I want you to understand, and it's electromagnetic induction, okay? We talk about a current being induced in the wire. Let's talk about what induction is, okay? So I've got, have I used any ink yet? Discard it. So I've talked about induction there, and I want to show you this in animation form, which is this. Okay, so this is, I feel sure I will have shown you guys this before, but it's from a website called PHET, P-H-E-T. I think it's the University of Colorado that does this, and they've got some insanely good animations for, well, for all of science, really, physics, chemistry, and biology. Okay, it's the kind of thing that you can have a play around with, and it doesn't feel like you're revising, but I assure you, you are revising, okay? If you play around with this long enough and start to understand some of these key concepts, because you get to play with the parameters and change them around, that's a powerful way of revising, okay? So first thing I want to do is, I want to show you that you move a magnet and it affects the magnetic field around it, okay? You can see that the magnetic field moves with the magnet, okay? So let's try this with a coil of wire then and understand what happens. If I move this magnetic field through this wire now, oh my god, what's just happened there? The electrons just moved. Electrons experience a force. It's called the Lorentz force. You don't need to know that. I think that's in A-level, actually. It's called the Lorentz force. Basically, a magnetic field moving near an electron causes that electron to move. It might be easier if you think of the electron having its own magnetic field around it. And that way, if I move a magnet near something with a magnetic field, it experiences a force, doesn't it? Okay. So if I move that through there, look at what happens to the voltage up here, though, or the potential difference. As I move the magnetic field through it, the magnet through it, notice how I was getting a negative voltage there. So electrons are moving in one direction, and then as I continue moving the magnet through, would you look at that? They start moving in the opposite direction. So I can make the electrons in a piece of wire move by moving a magnet. You could produce your own electricity doing this, and this is how we do it. We get a coil of wire, we get a magnet, we move the magnet near the wire, hey presto, electricity. Granted, there's not someone in a power station just waving a magnet at a piece of wire, but the principle is the same. I'll show you this with an electromagnet. So I've got an electromagnet there. It doesn't have to be a bar magnet. Like I've got a bar magnet there moving that. I can make an electromagnet. So I've got a cell there. Okay, so I've got a 10-volt cell, and you can see it's got a magnetic field around it because I'm passing a current through the coil of wire, through the solenoid. And as I move it, you can see the magnetic field moves with it. This is no different from using a bar magnet, is it? So if I put this now near a conductor, what's going to happen? Well, let's find out. So I've got a alternating current in this. I know this this is a bit of a step up. If I switch this to DC first, it's a bit easier to introduce it like that. So this is direct current. You can see the electrons are flowing through the wire in the same direction consistently. If I bring this now, which is essentially just a magnet, and I bring it near this coil of wire, oh, the bulb's just lit up. That's interesting, isn't it? Now this is great, but I don't really want to sit here and move this cell back and forth all day. I'd rather it moved itself. Can I get it to move itself? Yes. I can use not direct current, I can use alternating current. So I'm going to switch to alternating current now, right? All this big box at the top is showing you is the change in voltage in this wire. Okay, so you can see the electrons go one way, then the other, then the other, then the other, then the other. It's just showing you that it's going backwards and forwards. Now this is great, but my bulb's not lighting up. That's a shame, isn't it? It's just because this has only got one loop of wire in it, and the voltage isn't very high. So if I bring this a bit closer, you can see that, and I'm just going to take my hands off. Would you look at that? That bulb, albeit very dimly, is lighting up. The bulb's lighting up, and you can even see inside the coil of wire there, the electrons are moving a tiny bit back and forth. Not much happening there. If you were asked to make a generator and to produce electricity, and you did this, I doubt the person that asked you to do it would be very impressed. So they want a brighter bulb. They want the brightest bulb possible. How could you make this bulb brighter? Well, let's have a look in the tool tray down here on the right hand side. What options have we got? Now these are just for showing meters and electrons and fields and all that. I'm not really interested in changing that. What about this though? So pickup coil, I can change the number of loops and the loop area. Oh, I can even change the number of loops on the source. Let's try doing that first. So if I increase the number of loops on the source, so now I'm up to 4, would you look at that? That bulb just got a bit brighter. Why would that be? Remember, more coils of wire, stronger magnetic field. So this is now experiencing a stronger magnetic field, this pickup coil, because there's a stronger magnetic field being produced by the input coil, this one on the left-hand side. Let's try and make this bulb even brighter though. If I was to increase the number of loops on the right hand side, so I've got 1 loop there, there's 2. Oh, the bulb just got a bit brighter. 3, can't really tell much difference there. 3 is the maximum. What about if I make the loops bigger though? If I make the loops bigger, all of a sudden I've got a light there that's quite bright. Notice how those two things are not connected. If I move these away, there's no connection between that coil and that coil. There's nothing there. There's no connection between them. It is inducing a current in this secondary coil. So those electrons are moving back and forth because they're experiencing a force from the magnetic field that's being produced by the input coil, this thing on the left-hand side. By making an electromagnet and making it AC, so it's constantly switching its magnetic field, if I put a piece of wire inside its magnetic field, the electrons inside that wire are going to experience a force. Now that shouldn't be too much of a jump, because you know the wire would experience a force if there was a current passing through it. So there's a link between electricity and magnetism, okay? Hence the name of this topic, electromagnetism. I might give you a sneak peek of the generator there. Can you see how that works? Have a think about it. I'm not going to show you this. I'm going to do this in school, but just to get you thinking. Okay, so yeah, that was how a current is induced in a secondary coil, even though these two coils are not connected. So this produces a magnetic field around it. This wire is sat in that magnetic field, so the electrons sat in this wire experience that force as well and start moving backwards and forwards. Okay, and hey presto, I've now just induced an alternating current in my secondary coil. Perfect. Different number of coils on each one though. Interesting. The voltage induced in the secondary or output coil depends on the number of turns on the primary and secondary coils. So if you want to put a certain voltage and current in and get a certain voltage and current out, let's say for example you wanted a higher voltage out than you put in, if you put more coils of wire on the output side than you put on the input side, then there's more electrons being moved on the output side. More electrons, bigger, different voltage. Okay, so a step-up transformer has more turns on the secondary coil, and so it increases the voltage. If you look here on the output side, you can see that there's more coils of wire than there is on the input side. So if I put 10 volts on this side, I might get 20 volts out on that side. How is that even possible? We're making energy there, aren't we? Can't be created or destroyed, remember. We're not creating energy. If we're increasing the voltage, it just means we're decreasing the current, which is, well, the goal of a step-up transformer, okay? On the step-down transformer, you can see it's just the opposite. Whoops. You can see it's just the opposite way around. The input coil has more coils of wire on it than the output coil. We'd do this if you wanted to bring it back down from a high voltage and a low current to a low voltage and a high current. And we can tailor this to whatever situation we want. Okay, it depends on where the electrical energy is being supplied. What do you want it to be like? Use a suitable transformer and you can get whatever you want, whatever properties you want. Right, so transformers transfer power between circuits. Okay, so you've seen a circuit on the input coil and there's a circuit on the output coil. Electrical energy is being transferred from one side to the other. Okay, the design of a transformer determines the characteristics of the electricity flowing in its secondary circuit. The frequency of the alternating current in the secondary circuit matches the primary circuit. So if you've got electrons moving backwards and forwards 50 times a second, then the electrons in the other coil are going to move backwards and forwards 50 times every second as well. The only difference between them is how many electrons are being moved on each side, and that's what determines the voltage. So what is it about the voltage? What happens then? So in a transformer, the voltage in each circuit is related to the number of coils on each side by the following formula. So the primary voltage divided by the secondary voltage will equal the primary turns divided by the secondary turns. Now we can write this in a shorter version, and you've seen these on the specification, haven't you, that I showed you at the start, not the outcomes, what was in place of the outcomes. So we can write it like this. Voltage primary divided by voltage secondary is equal to number of turns on the primary divided by number of turns on the secondary. So if you've been given 3 of these values, you can work out what the fourth one is. Okay, so we're going to have a go at rearranging that equation in a second. There's a second one I need to show you first though. Okay, they not only change voltage, they change current. Okay, so if you look back at this equation is lovely, but it's only got voltage and number of turns. But current's involved in this as well, so how can we, if we're given a question that's got current in it? Well, we need a second equation for that, don't we? So they not only change the voltage, they change the current. For example, if the voltage increases, such as in a step-up transformer, the current decreases, which is the purpose. We want the current to decrease in a step-up transformer, don't we? This is because for any transformer, power in equals power out. Now, I said to you before, we're going to assume that all these are 100% efficient. They're not. Okay, so the efficiency varies from like 95 to like 99 point something percent. So they're still really, really efficient. But whenever you've got the transfer of electrical energy, there's usually heat involved. Okay, so there's always heat involved. And whenever there's heat involved, you're going to end up with a bit of heat loss. So there's a tiny bit of energy loss. But the amount of energy that's conserved when you're trying to transmit this stuff across the country, it is well worth that small amount of energy loss. Because otherwise we'd lose even more by not changing it. By keeping it at a lower voltage and a higher current, we'd lose way more in the lines than we would doing this, even if the transformer's not 100% efficient. So, power then equals voltage times current. We know this. P equals I times V. It's an equation we've used in the past. So if the power in is equal to the power out, then we can link this idea to that equation, and we can give this equation. The voltage on the primary coil multiplied by the current on the primary coil would equal the voltage on the secondary coil multiplied by the current on the secondary coil. Because this is how you calculate power, and power in is equal to power out. If I can change those two variables, if I increase the voltage, I decrease the current. What's your power? Let's say it's 10 watts. Okay, I can achieve that by a certain voltage and a certain current. On the other side, though, let's say that the voltage has dropped and the current's increased. Those two numbers, whatever they've now changed to, will still equal 10 watts. The power in is the same as the power out, which is great for us because then we can just change the parameter that we want. We want high voltage and low current as it's going into the national grid, and then we want to step that back down to a lower voltage and a higher current for use in domestic situations or factories or wherever it's being used. Okay, so that's the secondary equation there. Now, I'm not going to go through how to rearrange these equations with you because you've done it 100 times already, haven't you? You've either done it with me or you've done it in maths. We've done it before. However, I'm not assuming that you are perfect at it. So there's a quick YouTube video there specifically for this equation, how to rearrange this ratio equation. Okay, I've shortened the link. I know it looks a bit dodgy, but the YouTube link was massive. So I've used a URL shortener. So if you type that into Google, it'll come up with a quick video. All right, it'll only take a minute to go through. So have a quick look at that video if you're not 100% sure on how to rearrange this. The usual rules apply to this, though. The first thing I would do is I would write down what is it they're asking me for. Okay, so for this says, question A, to step down the potential difference from 240 volts AC, alternating current, to 12 volts AC, how many turns should there be on the primary coil if there are 20 turns on the secondary coil? Just read that again. How many turns should there be on the primary coil? Primary coil turns. Look at this. Primary coil turns. Number of turns on the primary coil. So what's it asking me for there? Number of turns on the primary coil. How are you going to work that out? Rearrange that equation to figure it out. Okay, yeah, pause the video, try that. How long is that going to take you? 5 minutes-ish, maybe? Give those a quick go, calculate some answers, and I'll get back to you in a second. Okay, answers incoming, so if you've not paused the video, pause it now. If you've done them, that's fine, we'll go through them now. Okay, so answers-wise, the number of turns on the primary coil would be equal to the voltage on the primary coil multiplied by the number of turns on the secondary coil divided by the voltage on the secondary coil. So if we stick the numbers into that, the voltage on the primary coil was 240 volts multiplied by the number on the secondary coil, which was 20 turns, so 240 volts multiplied by 20. Whatever the answer to that is, we then divided that by the voltage on the secondary coil, which is 12 volts. And then the answer we get for that one is 400 turns. And at this point, I want you to think about what we've just calculated. To step down the potential difference, how many turns should be on the primary coil if there are 20 turns on the secondary coil? We're stepping this voltage down. Alright, so there's a bit of a way. I've told you, I don't know how many times, the answer should feel right. We've just calculated that there's more turns on the primary than there is on the secondary coil. Is that right? It says to step down more on the primary than the secondary. Yes. Step down transformers always have more coils on the primary coil than they do on the secondary coil, or more turns on the input than on the output. Okay, so 400 turns is what you should have got for the first one. Right, for question 1b, it says if you fed 240 volts AC into a 100 turn primary coil of a transformer that had 10 turns on the secondary coil, what would the potential difference across the secondary coil be? So we're after potential difference, and we're after it on the secondary coil. Okay, so let's look back up here. Potential difference, it's one of these, voltage, and it's on the secondary coil, so it's VS. VS. Okay, well, I should have made the S smaller there. My mistake. So if you rearrange this equation to find VS, it's the number of turns on the secondary coil multiplied by the voltage on the primary coil divided by the number of coils on the primary coil. Yeah. Okay, so if you stick those numbers in then, so the number on the secondary was 10 on the secondary, so it's 10, multiplied by the voltage on the primary. If you fed 240 volts AC, if you fed it into something, so that must be on the primary. So that's 240 volts divided by the number of turns on the primary coil into a 100 turn primary coil, so 100. And that's just 100 turns, isn't it? Okay, so if you work that out, then the answer you should get is 24 volts. Okay, so hopefully that's making sense so far. Right, now we're moving on to using the different equation. Okay, the second equation. It says, assuming that the transformer is 100% efficient, we know it's not, but let's assume it is, the power output from the secondary coil would be equal to the power input from the primary coil. Power can be calculated using this equation, and it says power equals potential difference multiplied by current. We can use the fact that the transformer is assumed to be 100% efficient to write this, that the power on the primary is equal to the power on the secondary. So, the voltage on the primary multiplied by the current on the primary would be equal to the voltage on the secondary multiplied by the current on the secondary. And we've got all this from just saying that the power in is equal to power out. So how do you calculate power? Okay, work out power in, work out power out, they should be the same. Right, so what we need to do now is, it says we can use this equation to calculate the current drawn from the input supply to provide a particular power output. Use the information and equation to answer the questions. If the output of a torch charger is 6 volts, so we know that the power out is 6 volts. Sorry, the output of a torch, not power, the voltage out is 6 volts and has a current of 3 amps, that's the output, and it works from 240 volts AC. How much current is drawn from the electricity supply? Current being drawn is input current, okay? So we need to rearrange this equation to find what input current is equal to. Okay, so the current on the primary, I'm using input and primary interchangeably. Apologies if that's causing you some confusion. If I'm saying primary and you don't know what I'm on about, I mean, sorry, if I'm saying input and you don't know what I'm talking about the primary. Okay, so the input on the primary is the voltage of the secondary multiplied by the current of the secondary divided by the voltage of the primary. Okay, so if we stick those numbers in, the voltage on the secondary voltage, the output voltage was 6 volts, multiplied by the output current, which was 3 amps. Whoops, clicking buttons, I didn't mean to. It says 3 amps there, or it should do, 3 amps. And then we're dividing that by the primary voltage, so what voltage was put in. Oh, 240 volts, sorry, I couldn't see that. 240 volts. Okay, so if you calculate what that is, you get 0.075 amps. Right, so for question 2b, it says if the output of a mobile phone charger is 20 volts and 5 amps, and the charger runs from 240 volts AC, how much current does it draw? Okay, so it might be easier for you to pause and go, right, well, which one's which here before, because obviously I've just done that and had to pause myself and work out which one's which. Work them out before. The output of a mobile phone charger is 20 volts. So that's voltage and it's secondary. It's the output voltage, and it says the output is 5 amps, so that's current secondary. And this one, it runs from 240 volts AC, so that's the voltage primary. So what is it we're left with? VP, VS, IS, so it must be IP. It's the same equation as before. IP equals VS multiplied by IS divided by VP, and if we stick the numbers into that, VS was 20 volts, and then we're multiplying that by IS, which is 5 amps, which would give us 100, wouldn't it? And then we're dividing that by the primary voltage, which was 240 volts, and then if you calculate that, you get the answer of I did this earlier and it was 0.41666 recurring, but we'd round that, wouldn't we? So it'd be 0.417, so 0.417 amps. Okay, so hopefully that makes sense. I don't think there's anything else to go through there. Those are the ways you use the equations. You'll be given these again, remember, and you've just got to input your data and cash in those marks because you're given the equations. Right, what I want you to do now is there are a couple of exam questions there. It says 12 marks, so I don't think it'll take you 12 minutes to go through this because you're just labelling the first one. So pause it and give those questions a go, and I'll give you the answers in a second. Okay, answers incoming. Hopefully you've already paused it. Here we go. Right, so, oops. There's your mark scheme. So obviously we've got the labels for the transformer at the top and the marks for everything else there. And I think that's it. Right. If you've got any questions, obviously usual places, either on Google Classroom or put them on the YouTube video. I don't really mind. And then that'll be it. I'm not going to put any more up now. If you've got any general revision questions, or if you want me to go through something, I'm not going to do another full lesson. Obviously it's half term. I'm off as well. But if you've got any questions, you want me to go through something briefly, I don't mind that. Either send me an email or drop us a question or a comment on Google Classroom. Okay, that'll be it. Have a nice rest of the break. See you later.